Hello, and welcome to my Artificial Intelligence Fundamentals course. My name is Steve. In my professional life, I manage the Analytics Enablement division within a large enterprise organization, which means that my team provides all of the artificial intelligence technology for the data scientists throughout our organization to implement into their analysis and into their applications. This session is one I provided to various offices throughout our organizations on a handful of times, and I decided I would share it here more publicly. The intended audience is for folks who have an awareness of artificial intelligence, but perhaps not a deep understanding of it. So they'd like to demystify some of the key concepts. But more importantly, what we're going to endeavor to do here is to introduce some actual real-world implementations of how we use artificial intelligence so that you can kind of start ideating about, the art of the possible and how you might be able to use it in your own business domain use cases. So the way we're going to run through this is that we're going to just run through different artificial intelligence topics. I'll introduce them, tell you a little bit more about it. So for example, I might introduce natural language processing. That'll be our first topic. I'll explain to you what I know natural language processing to be, but then more importantly, I'll explain to you how we use it in our organization. Of course, I might have mentioned this, but if I hadn't, I'm definitely going to de-identify those specific implementations so that I don't introduce anything that might be proprietary or sensitive or otherwise controlled. So that's kind of the cadence of what we're going to do today. Again, it's going through these different key aspects of artificial intelligence, explain them, and then look at some implementations of how they're used in my organization. So, like I promised, we're going to start immediately with natural language processing. The reason I think natural language processing is a good place to start is because it's foundational to many of the other technologies that we'll be discussing throughout this session. So let's jump right into it. What is natural language processing, also NLP? It's a branch of artificial intelligence that enables computers to understand, interpret, and generate human language in both text and speech forms. So what does that mean? Your computer does not understand natural language. It doesn't understand the words that we're speaking. Your computer operates in numbers, more specifically in binary, ones and zeros. So when we are passing text to the computer, some key definition or some key terms for you to understand is tokenization, vectors, in this case embeddings, and the relationships that they form in high dimensional space. So let me explain that to you. So vectors are just numbers, right? And so when you talk or when you pass language to the computer, it takes your words and it turns them into numbers. The first thing it does is tokenizes that speech. It basically breaks down the speech into little components. Each of those components is called a token. A token might be a word, it might be less than the word, it might be a little bigger than the word. It all depends on the tokenization technique that you're using. Once they're tokenized, they're turned into numbers. And in this case, they're called vectors. These are like a list of numbers. And those numbers basically represent the characteristics of each of the tokens. In this case, we're referring specifically to embeddings because all of our vectors have a relationship in high dimensional space. So what does that mean? Imagine you have like a Cartesian plane where you have like an X and Y axis, but in this case on your graph, instead of just having two axes, you're going to have very many, more than probably the mind can comprehend. And then based on that, you can do very precise graphing of these vectors. So for example, this is the canonical example that people use when they're explaining vectorization, tokenization, the relationships amongst them, is that you might have the word king. When you graph the word king as a vector in high dimensional space, you put it on your graph. You could subtract mathematically from the word king its maleness or its masculinity. And when you subtract, actually do the mathematical operation of subtracting the vector that represents masculinity from king, you'll come to the location on the graph of queen. Because as you can see, a queen relates to a king as it's the same level of royalty, but it's missing the masculinity, right? The maleness of it. That's how vectorizations and tokenizations form natural language processing, is that they're making relationships amongst these words with a high level of fidelity because they're doing it with many, many characteristics in high dimensional space and then building relationships amongst them. So for me, what's so fascinating about artificial intelligence is that basically we have turned all of these semantic objects in the world into vectors. And once you vectorize all the semantic objects, as long as you can do mathematics amongst them, you can kind of define the behaviors and the relationships of them. Kind of my soapbox thing, I always talk about why I think artificial intelligence is so powerful, is because mathematics is like the language of everything that operates in the world, of all of physics. It underlines everything. So once we can leverage math with the large computational power that we have in like cloud computing, you can kind of start thinking about why the possibilities are endless. So that's basically the foundation of what's going on with natural language processing. You're taking language, you're tokenizing it, you're breaking it down into components, and then you're taking those components and you're turning them into numbers and you're relating them in high relational space, or high dimensional space, sorry. Another concept to know is named entity recognition. This isn't quite as core to it, but what named entity recognition does is that when you're going through your tokens, it basically can classify what each of those terms, each of those tokens means. So for example, if you had something like the pilot flew an airplane across or through the sky, named entity recognition would understand that pilot is the classification of a human. It's a type of human. The plane refers to like a vehicle. Those are classes. Those are entities. It's pulling out your entities from your text and it's classifying them so that it can do some little higher level processing on it. So that's at its core what natural language processing is. Some examples of how we use natural language processing. Again, NLP is fundamental to almost everything we do in artificial intelligence. So the use cases are endless. But in some examples, we do voice recognition of air traffic communications. We do document analysis. So, for example, we have maintenance logs that have open text fields where the technicians record their comments when they're reviewing equipment. They record those comments in open text field. You have to use natural language processing to make sense of that to make sense of those open text fields, and then be able to do further analysis on them. We also do predict from that sort of operation where you're pulling the information from the technician's logs. You can start doing predictive maintenance analytics. And we also, in our organization, we build lots of chatbots. Again, those chatbots operate in natural language because one, they're taking in prompts from the user that are in natural language, and they're also providing back responses that are in natural language as well. So that's a little bit about what natural language processing is. Here are some more concrete examples of how we're using it in my organization. One of the interesting things that we do is we do event analysis. So this is kind of complicated, but let me hopefully walk you through this. We have event narratives. The narratives are the natural language. And again, we're focusing on natural language for this aspect of the session. So say these events will describe some operation that happened or some event that happened in an operational space. Maybe a car broke down, there was a car accident, and the police reported the event analysis or the event narrative of what occurred in that car accident. We can take that description of the car accident. We then take what's called a taxonomy. A taxonomy, in this case, is basically it's a list of all of the potential causal factors that might have contributed to that class, or excuse me, to that event. In the taxonomy, each of the classes, each of the causal factors has a definition. So maybe the causal factor was like driver lack of attention, could have been vehicle malfunction, it could have been alcohol. And so for each of those classes, you then have a definition. And by having the definition for each of those classes and having the narrative that describes the event, we can send all of that in its natural language to a large language model like the ones like ChatGPT, which you're probably familiar with and which we'll talk about in more depth later. And we can actually run through and do what's called a binary classifier, going through all of the potential causal events and saying yes, no to each one. Was the driver's ability a causal factor? Was vehicle maintenance a causal factor? Was alcohol a causal factor? Yes, no. And then actually show the rationale for why our model made that justification of saying yes, no to each causal factor. This helps in safety analysis and doing like risk cause analysis or causal factor analysis of events. But again, the point we're trying to hammer home here is how natural language is core to that. Without the natural language processing, you couldn't do that at all. The process here kind of explains to you what I just described. On the slide, it says that we have event text data is ingested. So basically, you have the report of the safety event. Our large language model then processes the text data's natural language report. The large language model then compares the text data to each class in the taxonomy, utilizing a binary classifier, yes or no, to assess whether the event is associated with each class in the taxonomy. So that's a real-world implementation of how we're using natural language processing. It's also how we're using classification, something we're going to talk about a little bit later, and also large language models. Again, I referred to a little bit about how we use natural language processing in our predictive maintenance analytics. Again, that's using natural language to allow a model to understand the recorded notes that the technician collected when they were reviewing a piece of equipment, and then processing that natural language to be able to know something about the equipment. Maybe it's wear out date. Maybe you're trying to figure out why it failed. Well, you can take, because imagine this real quick. If you had a form for the technician where they were doing their review and every form was in a drop down where you had a list of values that the technician could select, that's very easy for us to analyze because there's a finite amount of values that the technician can select from when they're doing their review in the drop down. But when they have an open text field, they could write anything. It's infinitely limitless. In fact, they could say for the word transmitter, they might misspell the word transmitter, because say a transmitter might be a type of equipment that they're reviewing. They might misspell transmitter. They might use an acronym, shorthand. They might say XMTR. Natural language processing allows the computer to understand all of those derivations of that word and know that that technician meant transmitter in each of the cases that they used it. Again, there's a lot more to it, a lot more complexity to it than just natural language processing, but I'm trying to hammer home right now the core concept of natural language processing so we can better understand the subsequent technologies that are built upon it. So next thing I want to talk to you about, let's take a sip of my decaf coffee. And by the way, I'm just kind of shooting from the hip here, so I appreciate you all following through with me. I enjoy doing this. So next thing we're going to talk about is classifications. So classification is different ways that you can classify data. We're primarily going to talk about binary classification and multi-class classification. But before I can really explain to you what I mean by classification, let's talk a little bit about features and labels. What are features and what are labels? So when you're building a machine learning model, you're using data. Hopefully that's a given. Your data, each of your data inside your data set consists of features. Features are the characteristics that represent that data. So for example, if you're trying to do some prediction about the wear out of a piece of equipment, the features are the characteristics of that equipment. It could be the temperature that the equipment was running at, the room in which the equipment was stored, I don't know, the material that the equipment was composed of, all kinds of different things like that. They're literally the characteristics of the equipment. What are labels? Labels are the outcomes that you're trying to predict to. So for example, if you are in that equipment scenario, if you're trying to figure out, for example, you're doing a binary classifier, you're trying to figure out, does the equipment need maintenance? Yes or no? The label is the actual answer, yes or no. So your features, you'll use all your features about the equipment, and then it'll say that equipment that was running at room temperature, 68 degrees, that was stored in the correct storage facility, that had last been touched by so-and-so personnel, those are the features. It does need maintenance, yes. The yes is the label. To better explain what labels are, I'll give you an example. Say, for example, you're trying to build a model that's predicting or is trying to identify what kind of sickness a person might have. The features are the characteristics of that person or the symptoms that they're presenting with. So a person might have a cough, they might have a high temperature, they might have the sweats. Those are the features. The label is the sickness that they have. They have the flu, or they have a cold, or they have they have COVID, or whatever the case might be. Those are the labels. So when you're building a model, what you're trying to do is you're training the model based on historical data that has, when you're doing supervised learning, at least, and we'll talk about the difference between supervised and unsupervised learning. When you're doing supervised learning, you have a data set that has labels. It's historical data that has, for example, in the sickness scenario, it has different patient examples where the patient had these features and they had the flu, and this patient had these features and they had a cold. But you have many, many, many examples of that data in the data set, and you train a model to start, you remove the labels and you try to have the model predict for what it thinks the label should be, what it thinks based on the features the label should be. But you have the actual example, the actual label in your historical data. So you can tell the model how accurate it was. It was like, no, you were off. You said it was a flu, but it was actually a cold. But as you iterate through training the model over and over and over with that labeled data, it becomes increasingly more accurate. And so until such a case that becomes so accurate that you can start providing it unlabeled data, so data in the future. So for a future patient that we don't know what the sickness is, and it'll start predicting an output with some level of accuracy. So coming back to why I explained labels and features to you, was to explain what the different types of classifications are. We kind of talked about both of them already. Binary classification is when you're talking about 0 and 1, yes or no. So is the patient sick? Yes or no. Based on these features, is the patient sick? Yes or no. Based on these features, does the equipment need repair? Yes or no. Multi-class is when there's multiple outputs. So based on the features, what sickness does this person have? A cold, the flu. Those are multiple classes, multi-class. It's not just yes or no. You're actually producing which sickness that person or that patient has. There's also, this isn't the type of classification, but I always like to talk about here. There's also something called logistical regression. Logistical regressions is when you're trying to predict for an output that has a number on a continuous number line. So a good example for that is when you're trying to say predict the value of a house. And the features that you might have are the house's square footage, the year it was built, how many bedrooms it has, how many bathrooms, and you're trying to predict by logistical regression how much that home costs. So it's literally a number that on a number line could go from 0 to infinite. And so you run your model over and over and start to know, hey, houses that were built in a certain year with certain square footage in a certain neighborhood are probably $250,000, worth $250,000. That's a logistical regression, which isn't a type of classification, but I like talking about it here because it is a little bit of a different output than a binary class or a multi-class, and it always just seemed relevant to me to speak about in the classification section. So an example of a classification, again, take a sip, thank you. We talked about our predictive maintenance example a few times. So if you were to do, let's go back. Let me give you some context here. If we're going to do our predictive maintenance analysis, the features are the engine, the equipment temperature, its vibration readings, other telemetry, other observation reports. If you were to do a binary classifier, you'd be asking, does it need maintenance? Yes or no? Yes or no? 0 or 1. The multi-class, the outputs would be like, it's operating normally, or it's having bearing wear, or the seals are degrading, or something like that. It's predicting multiple class outputs. Going back to the example I talked about earlier, where we had our event analysis using a defined taxonomy, that in the example of how we've implemented it in our organization, we use a binary classifier. We have the event narrative, and then we have our taxonomy of potential causal factors. And we're going through each causal factor as a binary classifier saying yes, no, yes, no, yes, no. We could have done it as a multi-class. We could have done it to where the model analyzes the narrative and then tells us which class or which causal factor was associated with that event. We happen to do it as a binary classifier going through a defined taxonomy, but there could have been an implementation where we did a multi-class output. So hopefully you can see the difference between the two based on those examples. Real quick, I want to take a pause and just give credit. I am not a creative person. I manage a data science team, so I just want to give credit to the folks that I got this free background from for our presentation. You can see the link on the screen. You, of course, can't click the link, but it's from the website called FreePick. So I did want to provide credit to them for providing this nice background that we're using for this session. With that, we'll move into our next topic. We're going to talk a little bit about neural networks. What is a neural network? Well, first, let's talk about how we train neural networks. Let's talk a little bit about supervised learning and unsupervised learning, because I think from understanding those two concepts, you can start to extrapolate what a neural network is. Other than telling you the most important thing about a neural network is that it's composed of many, many layers of analysis or of sort of parameters within the model that come together to form a model of understanding that can produce new output. But again, this will make more sense to you if I tell you about supervised learning and unsupervised learning. So since we talked about labels and features, we can now talk about supervised learning and unsupervised learning. Supervised learning is that example I had just talked about, or I've mostly been talking about throughout this session so far. It's when you're training a machine learning model, in this case, a neural network, using historic labeled data. Again, that's like the example of the patient and trying to identify what sickness they have. The historical data that you'll train the model on when you're doing supervised learning is data where you know what sickness that patient had. So that's how you train your model in supervised learning, is that you know what the outcomes were and you're trying to see how close your model is to predicting the right outcome. And then using something called a gradient function or loss function, you're going through and you're trying to optimize the model to become more and more accurate during each training run. But you have to have labeled data to do supervised learning. The example we have here is an image classification where photos are labeled dog or not dog. So basically, you will train the model on a bunch of images. Some of the images are dogs, some of the images are not dogs. The labels will say dog or not dog, and the model will try to predict, is the particular image that it's analyzing, is it a dog or not? When it's wrong and it says it's a dog and it's not, we do reinforcement. We tell the model it's wrong. We adjust the weights, and basically the model goes back through and it continues to iterate through its training, through reinforcement learning, until it gets closer and closer to predicting that the pictures of the dogs are in fact, or it's the ones that it calls dogs are in fact pictures of dogs. Unsupervised learning is when you do not have labels for your data. This is more when the machine itself is given a large data set and it's just analyzing and identifying patterns amongst that data without labels. So an example for that would be, a key example would be shopping behaviors, or I think of like viewing behaviors. So say you have a video streaming platform and it doesn't have any historical data about you, the user, but as you start using the service, as you start selecting videos, it starts to identify how the features of you, the user, and how you compare to other users throughout its ecosystem and the similar features that they have. And it can start identifying patterns and say, okay, because you watched this video, and then that video, and then that video, you match the pattern of this other user who is similar to you and has features like you. And therefore, it can start predicting from there what it thinks you're going to want to watch next. So again, the difference there is in supervised learning, you train the model on labeled data. On unsupervised learning, you do not have labeled data. The model is kind of learning as you're presenting more and more data to it, and it's identifying patterns sort of on its own. So again, the key difference is supervised learning requires labeled data. Unsupervised learning finds patterns independently. Now, all of this is to describe to you what a neural network is. So neural networks are a type of deep learning that, and I can give you an example to kind of hammer home how they work. Or what they are. One type of neural network is a convolutional neural network. Those are the ones that examine images. And the example that we have here on the slide is that there's a convolutional neural network that can look at medical imagery, like say MRIs, and it can basically, through its neural network, through its many, many layers, it has all these layers where the model is basically, it has these layers. It's basically analyzing the image. It's breaking the image down into smaller pieces, almost or all the way down to its pixels. And then it's able to make some analysis from the model's training and then make predictions about what that image might be suggesting. So in this case, they're trying to determine if a person has cancer or not. And they found in this particular study with 93% accuracy that using a convolutional neural network, they can look at MRI data, and the convolutional neural network can say that this person does or does not have cancer, it is malignant or it is benign. And again, it's using that neural network, that very complex, many multi-layered model to make that determination and that outcome. So the most common example of neural networks that I think most of us know as being ubiquitous are large language models, such as those that we use in ChatGPT or Claude or any of those products like that. And let me explain some of the types of large language models that there are. There's something called a foundational model. A foundational model is the large language model that is provided by the vendor that is trained on vast amounts of data. Models like OpenAI's GPT models, Vicuna, Mistral, all of these large language models are trained on basically a corpus of data that's as wide as the internet over a certain time period, trained on using many GPUs, large amounts of computational power costing millions and billions of dollars. What's unique about a foundational model is that a foundational model can generate new output. And as we'll talk about here in a couple slides, what kind of makes generative AI unique from traditional machine learning is that generative AI isn't just specific to one task. It's been trained on so much data that it can do many things. Like you can ask ChatGPT to write an email for you, but it could write an email for you, but it could also maybe do some other sort of analysis for you. Whereas that's a little bit different from traditional machine learning, where the models typically have one specific output or one specific task. And I'm noticing that I'm kind of disappearing on the camera here. It's kind of freaking me out, but it's okay. So that's what a foundational model is. And foundational models are open source or closed source. When they're open source, which means that the model's weights and parameters are available to those of us in the community that we can tweak, that means that we can fine tune the model. What does that mean? When you fine tune the model, you give it domain specific data so that the model starts to know some certain things specifically about your business domain. So for example, I work in aviation. We might take an open source foundational model and fine tune it on aviation data. And now when I ask the chatbot questions, if we are using a chatbot, for example, it's more likely to give me an answer relevant to aviation than something else because it's been fine tuned on aviation data. You can only do that with an open source model because closed source models, the weights and the parameters to the neural network aren't provided for manipulation. And now I'm a complete ghost. I just disappeared off the screen completely. But that's okay. You don't need to see me. Just stick with the material. That's more important. So that's fine tuning. That's tweaking the model with domain specific knowledge that makes the model a little bit more tuned to your particular business domain. Additional technique that we utilize to great success in my organization is something called retrieval augmented generation. What this is you don't fine tune the model, and you can do this with a closed source model. You don't fine tune the model on any specific domain information. What you do is you provide domain specific information into a repository. And let's say you're doing a retrieval augmented generation, it's usually associated with chatbots. The way it works is that when the user presents their question with a prompt, that prompt first queries the documents that you uploaded. So let me take a step back. In our case, we provide chatbots to who we call the chatbot owners. They are people in their business domain, say human resources. The chatbot owner in, say, human resources would upload all of their human resources documents to a repository. When the chatbot users then send a prompt to the chatbot, instead of going straight to the large language model, it first queries the human resources documents. It finds the text that's relevant to the prompt. It then sends the prompt and the relevant text to the large language model. The large language model does its reasoning. It then provides or should say its reasoning. It does its inference. It then sends a response back and presents it to the user as the answer. So the response is grounded in that documentation that was provided by the chatbot owner. That's called retrieval augmented generation. And that allows you to provide some domain specific knowledge without actually fine tuning the model. Let's talk about how large language models work. A little bit about how they work, and there's many facets of how they work, but the two that we're going to specifically talk about right now are context and the attention mechanism. So what is context? Context is the model's, we'll call it working memory, whereas attention is the model's focus system. I like to think of context as a sliding window. So as you're putting input to a model, there's a window of finite length. And as your input exceeds the length of that window, and the window is sliding towards the end of the input that it's continuously sliding to the end of the input that you're entering. If your context window isn't big enough for the extent of your input, it's going to start basically, quote unquote, forgetting what you entered at the beginning. That's the context window. There's only so much input within that window that the model can basically associate in its inference. That's why when you go to a website like ChatGPT, you can't just enter a prompt that's endless. At some point, it'll cut you off. And even when you start having conversations, it might give you a warning and say, hey, the fidelity of your responses are going to start diminishing. It's because you're exceeding the context window. You're putting in more input, so it's only recalling the most recent things you input, and it's forgetting the things at the beginning that are outside the context window. Within that context window, the large language model uses something called attention mechanism to make sense of every word. Remember, way back at the beginning, we talked about vectors, embeddings, and tokenization of each of the components in your input. Recall is a token. What attention mechanism is making sense of each token in the context of the tokens that surround it. So let me kind of drive that one home for you. Consider the word bank. The word bank can have multiple meanings. It could be a financial institution. It could be the land next to a river. It could be the verb that you do when a ball bounces off the backboard in basketball. Those are all ways of using the word bank. What the attention mechanism does is it assigns weight to each of the words within the context window, and then better understands the word bank based on the relationships and the weighted relationships it has with the other words within its context window. So if you happen to use the term money and teller and credit card, it's gonna infer that your use of the word bank in this case means a financial institution. That's what the attention mechanism is doing. It's making sense of the specific implementation of that word based on the weighted relationships of the tokens within its context window. So an example of that in my domain is say you have an air traffic control communication that says cleared to land 27R. If you had no other content, if there was nothing else within the context window that gave the attention mechanism some meaning to that term, like if you didn't have the necessary context of previous messages showing aircraft call sign and position, some conversation about active runways or airport procedures, the model might not know what cleared to land 27R means. It might not know that you're referring to the runway 27R and that cleared to land is a direction from the air traffic controller to the pilot. Large language models now are so well trained, they'll probably infer that even if you didn't have other context. But for per this example, to make it really make sense, if you had a lesser trained large language or a lesser trained model, it would need the surrounding context for the attention mechanism to make sense of clear to land 27R. So hopefully that gives you a better understanding of what the context window is and how the attention mechanism works within the context window to make sense of each specific word, how the model makes sense of each specific word. So now let's talk a little bit about machine learning, artificial intelligence, and generative AI. So traditional machine learning are algorithms that learn patterns from structured data to make predictions requiring manual feature engineering and specific task training. Many times when we talk about traditional machine learning, we're talking about supervised learning and the methodologies I explained earlier, where you're training a model on labeled data to predict outputs that accurately match the labels that are provided. And keeping in mind that traditional machine learning algorithms typically do one thing. So for example, I talked earlier about having a model that predicts a house's value. In traditional machine learning, a machine learning model does that one thing. It will just predict the values of a house. It won't do anything else. I really wish this video worked. Maybe I should sit closer. So that's one thing particular about traditional machine learning. That's not always true, but it's usually the case that machine learning models only do one specific task. What is artificial intelligence? Artificial intelligence is a subset of machine learning that reminds humans of human behavior. But it's important to not personify artificial intelligence, because artificial intelligence isn't actually doing any human reasoning. It's at its core, it's doing a mathematical equation, kind of like I described to you earlier when we were talking about vectors in high dimensional space. It's basically doing on your GPU. The reason you need a GPU to run these massive large language models is because they're doing parallel processing of many thousands of matrix multiplication simultaneously. So basically, it's just doing this enormous amount of multiplication to be able to produce inference and predict what's the next token that it thinks is sensible in its response. That's all it's doing in most of these models. These models are just doing mathematics in the back end for most models, but what they're definitely not doing is human-like reasoning. However, artificial intelligence gives the perception that these models are doing human-like things. That's what artificial intelligence generally is. What is generative AI? Generative AI are models of artificial intelligence that have been trained on so much data that they can start to generate their own like sui generis output. They can start generating things that were not within their training data. So, for example, with like the canonical example, if you go to ChatGPT, you can ask it to write you a poem in the style of Shakespeare. It may produce a poem that never existed in its training data, but it's been trained on so much data. It has such strong inferencing power that it can produce new content that is totally original. That's why it's generative. That's what generative means. Also, generative AI, they tend to be so well or so massively trained that they can do multiple tasks. So, where I mentioned that machine learning is usually interested in performing one specific task, you might ask ChatGPT if you gave it the features to a house, it might be able to predict for you the value of that house. But you could also ask it to write you an email, or you could also ask it to do several other things. That's what makes generative AI, the most unique thing about generative AI is, of course, that it generates original content, but also it's different from machine learning, traditional machine learning, that it oftentimes can do multiple things. So again, hammering home, the key differences are that traditional machine learning is task specific and is trained on structured data. Artificial intelligence encompasses all intelligent system behaviors, whereas generative AI creates new content. I put new context, it should be new content, and has more general purpose. Let's talk about some of the modes in generative AI. What are we referring to when we say modes? Modes refer to the different type of content that models can create. So maybe the mode you're most familiar with is text generation. Those are text models. The mode is text. And within these models, like I talked about earlier, there's open source and there's closed source. Closed source is where, as developers, we do not have access to the weights, the parameters. We don't have access to the inner workings of the model, and we can't tweak the model to behave specifically how we'd like. Whereas open source, we do have access to the parameters, to the weights of the model, and we can tweak them, and we can make the model behave in certain ways for our particular use case. But the mode, again, is the output that the model produces. So, for example, ChatGPT is a text mode. It produces text. You also have the mode of image. You have models that produce images. For example, in closed source examples are DALL-E and Midjourney. You provide text as their mode, they produce images. You give text saying, hey, provide a very dark, evil, demonic image of something, of a gargoyle, and it will produce an image that is a representation of the text that you provided. That's the mode of image generation. An open source example is Stable Diffusion. When it's open source, we can start manipulating the weights and the parameters so that, let's say we want the model to always make all of our image outputs to be a little bit more cartoony. We can tweak the model so that every time, we don't have to tell it with each prompt, to make the output, the images more cartoony. We'll actually tweak the model so that every model or every image output that it creates will be a little bit more cartoony like. That's the advantage of having open source versus closed source. Some models, another mode is code generation. These are for developers. These models are trained on software coding projects or development projects. So they've been trained on many lines of programming code. And so they can help developers write code. So GitHub Copilot is an example. StarCoder are examples. These you can go into in your integrated development environment, in your coding environment. You can start writing code, and it's going to like autocomplete your code based on its training. It's been trained on so many examples of code. It knows when you start writing a function, it's seen similar functions in its training data, and it will start to autocomplete your function, the code that you're trying to generate on your behalf. So that's another mode, code generation. You can even go like GitHub Copilot, you can tell it without autocomplete, you can say, hey, create a function that takes a string, that outputs an object, that does such and such logic within the function, and it will, based on its training, it will know what you're trying to do, and it will produce that code. That's a mode of a model, it's code generation. Another mode is audio generation. You provide text as an input, you say, produce audio that has a certain type of beat, it has a snare on every third beat, and it's of the genre techno, and it'll produce audio that matches the text input that you put in. Again, there's closed source, And then there's open source, where we can manipulate the model so we can change the type of output that it produces each time. All right, we're almost getting done here. We're almost finishing up. I think we're on one of our last slides. One of the things to be aware of that some of these generative AI models are capable of producing are called hallucinations. The things about generative AI is that more than likely, unless you have filtered the model in certain ways, unless you put in certain safeguards, it's not going to tell you when it's incorrect. It's going to produce, when it produces a false output, it's going to have just as much confidence as if it produced an accurate output. So you as a user won't know necessarily that it had hallucinated. So you might say, who was the president in 1984? And it would very confidently say George Bush, when the case might have been that in truth, the president was Ronald Reagan. But it's not going to give you any indication that it was wrong. That's called a hallucination. That's why in our organization, we say any output of artificial intelligence needs to be validated by a subject matter expert, because, again, these models are not 100% accurate. Referring back to the methodology of retrieval augmented generation that I talked to you about those chatbots that reference uploaded documents, one of the values that they provide is that it's easier to validate whether your model had hallucinated. For example, the technology that we use to build most of our chatbots, we use Azure AI. Azure AI as a service, when it provides the response for your chatbot users, it provides a response with a citation to the reference documents from which it pulled its information. So the user can literally click on the citation and it'll pop up the reference document, and you can actually validate if the response that you're reading is actually within the documentation that it was referencing. So that gives you a way of validating whether the model had hallucinated or not. But that, again, is only available when you're doing retrieval augmented generation. There's other ways of validating for hallucinations, but I just wanted to elaborate a little bit on the RAG use case right there. Going back, I did want to give a couple examples of the RAG chatbots that we're building. I told you about like the human resources example. You could say if you work, you might understand if you work at a large enterprise organization, your human resources department may have many policy manuals, and you have a very specific question like, am I authorized to work remotely? You might not even know what manual to look in. The benefit of retrieval augmented generation is you can ask that natural language question, am I eligible to work remotely? It'll query all of the human resources policies. It'll then send the relevant text from those documents to the large language model and then provide a response back and says, yes, because of your characteristics, you are able to work remotely. And here's the document that we base that answer on. Another example that we built in our office is for our technicians. They have many equipment manuals that are hundreds and hundreds of pages long. And they might need to know, for example, how much voltage can go through this particular circuit. And instead of having to go through that entire document and finding the one diagram that has that data in it, they can ask the question to the chatbot, how much voltage can go through circuit such and such in equipment XYZ, and it'll query all of their equipment documentation, again, send the relevant text to the large language model, then provide a response back that says, such and such voltage can go through that circuit in equipment XYZ, and here's the reference tech manual that we pulled that information from. So there's just some examples of the retrieval augmented generation chatbots that we're building in our organization. And we're going to finish this up today by giving you two quick art of the possible examples of how you can use artificial intelligence. These are just super random. Let me talk about the second one first because it's the one I'm less familiar with. But one of my data scientists on my team, and I don't want to speak too much about this because it's his project, but it's immensely interesting. He wrote his master's thesis using artificial intelligence to basically run models through video games. They're called platformer video games. So platformer video games are like ones where there's like basically a map and you have to go from one place to the other, and you have enemies, you have, like Mario Brothers, you might have like traps and pits you can fall into, and at the end you have to say capture the flag. He was able to use artificial intelligence to run many simulations through the game. Before having this methodology, people would actually have to play the game over and over and record their insights from their experience playing the game and say like, oh, right here, I always fall into the pit. He was able to do like a heat map that said when the model runs through the game, it typically hits the pit right here. So this part of the map is particularly challenging. and he used reinforcement learning so that every time it did the model did something positive, it was rewarded with a positive score. And when they say like the model died in the game, it would be reinforced with a negative score. And like in the Mario Brothers, you have the little coins. When it would get a coin, he would reinforce it with a positive score. When it ultimately captured the flag, it would get a very high positive reinforcement. He was able to do this over and over and over to where he could show what levels in the game are challenging, where they have flaws in the game, and basically do quality control on the video game development process using machine learning. That's interesting to us, not because I work in the video game domain, but we are able to extrapolate that using simulations in the same way in the aviation domain, you might be able to run simulations of an aircraft coming to a runway and determine based on certain features, again, we talked about that earlier, whether an airplane is more likely to abort its landing and have to do like a rejected landing and do a go around, or if it's likely to land. We can start simulating and seeing like what are the weather conditions that are more likely to cause an aircraft to have to abort landing. What are the runway conditions that are contributing to aborted landings and stuff like that. So that he is able to explain to our workforce this totally different use case that he did for his master's thesis, but we're able to apply it to our own work just by doing a little extrapolation. And in a real world use case that when I first started dabbling in using generative AI as a software developer, the use case the very first one I probably did is that every single morning I get a bunch of news aggregators. I subscribe to this news aggregator called TLDR, which I don't get anything from, but I really love. So I want to advocate for all of you to subscribe to it if you are into tech. TLDR are all these different volumes of, say, like cryptocurrency information, artificial intelligence information, ongoings, and like that are relevant to business founders, venture capitalists, and they're an aggregator. So they have all these. Each volume has a bunch of other a list of other news stories that it links to. Every morning, I would open up all of those links in tabs and intend to read them throughout my day, and would never get around to it. So I'd always just never read the information I intended to. So when I asked Claude, the type of artificial intelligence that I prefer to use myself, I went to Claude and I said, hey, provide me a Python code that will log into my email server after I authenticate. It will download the day's mail, the day's email. It will filter for those that have TLDR in the subject line, and then it will take all of the content from those emails, concatenate it into a text file, save that text file to my hard drive, strip out all the extraneous information, all the URLs, everything, like use a regex, a regular expression, to take out all the stuff I don't want, that's just extra information, and then invoke artificial intelligence to turn the text into speech and save the file as an MP3. By giving Claude that prompt, it literally produced the Python code that I needed to create that little application. All I had to do was paste it into my Visual Studio Code, my VS Code, the coding platform that I use. Initially, it had some errors, but the cool thing about AI is that you can literally say, hey, on line 63, there was an error. I was expecting, a string, but there was a null value. You tell Claude that, the AI, and it says, yes, you're right, and it literally fixes its own code. You iterate like that a few times, and eventually you'll get to working code. So basically, I no longer had to develop that app. I basically became like a human debugger without actually having to develop the app. You can even go into a level of complexity further. If you're a developer, you might recognize that we do unit testing to ensure that the logic in our code is sound. You can actually have artificial intelligence write unit tests for the code that it produces. Again, in the production space, there's a lot more rigor to this. This is my own personal project. In the production space, you have code review, you have a development, you have version control, you have all these different processes to ensure that your code is at a high level of quality. But as a personal project, this worked out perfect. And ultimately, it produced a Python file that I can run in my terminal that every single morning now, it goes into my email, it downloads those files to my local hard drive, and it produces an MP3 podcast of those TLDR newsletters that I get every morning. So now I actually listen to them instead of not reading them, like had been the case earlier. And all of that took me maybe 40 minutes, where developing it may have taken me a few hours in the past as a developer. So I hope this session taught you a little bit more about artificial intelligence fundamentals. If you want to know more about me, that's my name. You can find me on LinkedIn. I'll hopefully put up some more videos about some different other aspects of artificial intelligence. I have one plan where I'm going to talk about enterprise data management and the way we do our data architecture, our data warehouse, our analytics platform at my organization without getting into anything sensitive. That's on the slate as next. But for now, I hope you are interested or you got some information about artificial intelligence fundamentals, and I really appreciate you sticking through this whole video. Thank you, and I'll talk to you all later.